Okay. Yeah, so my name is Tooby Smith. I am currently at the University of Bath, and I'm going to be speaking to you about a project that I'm working on called PhysLean. Before I get into what PhysLean is about, although you can probably guess by the title, I want to tell you a story. And for this story, I want you to set yourself back to the late 1800s and early 1900s and pretend you're in the social clubs of the time speaking to your academic colleagues. There's an equation going around, and this equation predicts this curve. It predicts that as x goes to 0, y goes up to infinity. It's a perfectly valid mathematical equation. There's nothing wrong with it. The problem is, in these social clubs of the late 1800s and early 1900s, people were given this equation some physics context. They were saying it predicted the radiation emitted by a black body. So an example of a black body is something like a torch, which I've got here, or something like the sun. So what this curve says is that as the wavelength of the radiation decreases, the energy emitted by that black body increases up to infinity. In other words, that when I turn this torch on, because it's an example of a black body, it will emit an infinite amount of energy. You all know that if I turn this torch on, that's not the case. Otherwise, we wouldn't be standing here. This really illustrates the difference between physics and mathematics. The mathematical context of this curve is the fact that it, for example, goes up to infinity as x goes to 0. Whilst the physics context is the statement that it corresponds to black body radiation. In fact, the fact that this doesn't actually correspond to black body radiation, and that was a mistakenly given physics context, was called the ultraviolet catastrophe in the late 1800s to 1900s, and it is what led to the discovery, or one of the things that led to the discovery of quantum mechanics. With this viewpoint, and with this distinction between the mathematics context, the curve, and the physics context, we can give a clear separation to what it means to do physics and what it means to do mathematics. On one side, you've got physics, where you care about both the mathematical context of the theorem and the statements, as well as the underlying physics context. Those are the additional words that you apply to that and the additional intuition that you apply to that. And on the mathematics side, you only really care about the mathematics context. Of course, this viewpoint goes against this traditional viewpoint of a spectrum between mathematics and physics. Most people that work on interactive theorem provers very much focus on the mathematics side of stuff. And that is because interactive theorem provers are very good at including this mathematical context. In fact, they let you include it without making mistakes. They check what you are doing. My personal background is, you can probably guess, in physics. And so when I started to learn about interactive theorem provers, I was naturally interested in formalizing physics and including both that mathematical context and the physics context into the results. So about 2 years ago, I made this project. It was initially called HEPLean, which stands for High Energy Physics Lean, but now it's called PhysLean. And this is an open source community project to digitalize results from physics into Lean form. It's trying to be the akin to MathLib, but for physics. So it's a monolithic library for physics results where all of the results are interconnected with one another. Let me quickly mention this community part. This isn't just a me project. There have been 20 contributors to the project, and this is a bit of a number that doesn't really mean anything, but there are 100 people on the Sulip channel, or over 100 people on the Sulip channel. So it's not just a me thing. There's other people contributing it to themselves, to it as well. So given this is a physics project, the key question is, how do we include the physics context within the project? Including the mathematics context is obviously very simple. You copy what's done in MathLib and what is done in all of these interactive theorem provers. You write definitions and you write theorems. But if you want to include the physics context, you have to be slightly more clever. So the first way we do it is through the organization of the project. So if you look at MathLib and you look at the files within MathLib, it's going to say stuff like group theory, differential geometry, topology. Whereas if you look at the files within PhysLean, they match what is typical of a physics undergraduate course. You've got things like classical mechanics, condensed matter theory, optics, particle physics, quantum field theory. You have this mathematics file, which is for API around some mathematics stuff that's in MathLib, but we kind of need a more physics-friendly version of it. So that's the first way we include the physics context, by organizing and structuring the project such that the physics is there by default. The second way is through names of definitions and theorems. So I've given an example here from a file on the Higgs boson. The Higgs boson was the last particle that we discovered at the Large Hadron Collider in 2012. It is what gives most things in the universe a mass. And you can see here that we have this thing called Higgs spec, and that is just the Euclidean space or the two-dimensional complex vector space. But by calling it Higgs spec, we indicate to the user that this corresponds to the vector space, or this should be used as the vector space, the target vector space of the Higgs boson. The Higgs boson corresponds to a field which lands in C2 as a vector space. And there are other examples where this vector space appears the same mathematical which has the same mathematical context, but applied with different physical context. So this vector space also appears, for example, in the Hilbert space of a qubit. If you know anything about quantum information theory and quantum computers, they're based on these things called qubits. The Hilbert space of a qubit is exactly the same vector space, but it has the different physical meaning once you give that physics context applied that. And in an ideal world, you would define things such that you can't cast between the two different definitions with physics context, or two different objects which have the same mathematical definition but different physics context. This isn't done here, so I'm not going to dwell too much on that. The third way we include the physics context is by documentation, and this is something that I personally have been working quite hard on recently. That is to include documentation that explains the underlying physics context and tells the story that you would see in physics lecture notes or physics papers. We'll see later that physics papers tend to be written in a very different style to mathematics papers. They tend to be more wordy, more written in terms of prose rather than split into definitions and theorems. And that is because this is what the physicists are used to. They're used to reading the story that tells you and motivates where things come from. And this is precisely what we're trying to do here. You can see there's a table of content, and that kind of splits the file up. And each of those headings has a description of what is in that section. This currently isn't prolific within the projects, and this is something that we are trying to work on. The fourth way we include physics context is through references. Obviously, projects like MathLib have references to the literature, but with a project like PhysLean, you can't obviously put all of the physics context within the project. That would be akin to just reproducing the physics literature into the project. So including references that allow people to go out of the project and look and see what's happening within the physics literature and get a better understanding of why the theorems and the definitions are being proved within the project. Good. So at this point, if I was sitting where you all are sitting, I would probably have 4 questions. And these are really 4 questions that you could apply to any project on really anything. Who is the project for? What has already been done? What are the challenges? And what does the road ahead look like? So I'm going to go through each of these questions in turn, and really this is going to take up the bulk of the rest of this talk. So let's answer the first question. Who is this project for? Well, why is this an important question? It's an important question because if you don't meet the need, if you don't think about the audience and their specific needs, you build a useless project. If you don't think about who are we making this project for, who are they going to be, who are the stakeholders of this project, who is it going to benefit, then you build a project which doesn't really have any use for anybody. And there are some examples of these. These are a bit tenuous examples, but there is this project called Google Wave and Microsoft Soon. Google Wave was a all-encompassing, let's say, communication platform in the late 2000s and early 2010s that let you write wikis, emails, to-do lists, and all of that sort of stuff. But Microsoft Soon was a competitor to Apple's iPod. And you could argue that these two really missed the needs of the audience, making something that was too complicated for their users. So who are the target audiences of, or who is the target audience of the project PhysLean? Well, you can probably guess that it is the average physicist. And it's important to note that different rules of engagement apply when you're speaking about the average physicist compared to when you're speaking about the average mathematician or the average computer scientist. In particular, physicists have never been taught how to prove things. They don't know what a proof is. They rarely are taught things like induction. Physics papers don't contain proofs. So introducing and making an interactive theorem proofer, which is, as the name suggests, all about proving stuff, making that of use for the physicists is obviously more difficult and slightly different rules apply than if you're doing that, for example, for mathematicians. So what does this mean in practice? What does this mean we have to do to make sure that the project is suitable for the physicist? So the zero point, and this is what I've already mentioned, so I'm not going to dwell too much on it, is that you include the physics context within the project, that allowing the physicists to understand what is in the file from their perspective, not from the perspective of a mathematician, but from the perspective that they have grown up with, that they have understood and they've been taught through their undergraduate or master's or research. The first way is to use the right terminology. So if I was in a room of people interested in interactive theorem provers and I said, I'm formalizing physics, your minds would go to the fact that I'm writing physics into an interactive theorem prover. But if I say I'm formalizing physics to a physicist, they are going to assume that I am axiomizing physics. They're going to assume that I am making a rigorous mathematical formulation of physics based on some unifying theory. And I want to make it very clear that PhysLean is not about that. PhysLean is about formalizing in the sense that interactive theorem provers people say formalizing, to write the physics that we're currently doing at research level into an interactive theorem prover. Which means that when I talk to physicists about PhysLean, I don't use the word formalizing, I use the word digitalizing, because then there's no ambiguity about what that means. The second thing is to use computable functions. So as we saw yesterday, within Lean, you can write non-computable functions. And this occurs if you have things like classical choice. Physicists like writing programs. They like writing simulations. They like using things like Mathematica to compute stuff. And by having computable functions, you allow them, you have bridged that gap from the sorts of software that they are used to something like Lean. Obviously, this is not always possible. For example, if you're using the real numbers within Lean, it's very rare that you'll be able to write computable functions. But there are cases where one may be tempted to just put non-computable around all of your definitions in a folder. But if you think a bit more carefully about it, you can make things computable and you can make things nice and easy for the physicist. The third point is to reference experimental data. Physicists obviously care about the real world. That is really what this physics context is guided by. This physics context is guided by. It's guided by experimental data. The fact that when I turn this torch on, it doesn't destroy the world, predicting that equation at the start that that curve was wrong. So having some reference to experimental data, whether that be within the documentation, or even better, whether you can include that into the theorems or the definitions themselves, or into the Lean code itself. Then the fourth point, prove things in the way that physicists do. And I know I've already said that physicists don't prove stuff, so this is probably a bit of an oxymoron, but if there is a way that physicists prove stuff, or if there is a theorem in physics that the physicists derive in a specific way, perhaps because they are being guided by their intuition, aim to follow that way instead of the way that the mathematician would naively perhaps prove that theorem in a single line as a corollary of a general case. Because if you prove things in the way that a physicist does, you get all of the API that the physicist may need to do other things. Good. Okay. So that kind of concludes the first question, who is this project for? And the answer to that was, this project is for the average physicist. Yeah.
Will you show examples of what it means to prove things in the physics way?
I will, but I can talk about it later if you want. There are, for example, okay, let me give you a brief example. There's this theorem called Wick's theorem in physics, and Wick's theorem is the precursor to these things called Feynman diagrams. You can derive Wick's theorem by assuming things like, or by using probability. It's basically a statement about expectation values of things. So you can either get there through probability, or you can get there from the way that the physicists would get there, which is defining a field operator and the things that are related to the underlying physics and deriving it that way. I know that's not particularly very clear. But... Okay, so
do you target students?
Yeah, so yes. So we've done a lot of work. So we've done two bits of work, sides of this. One side is, formalizing research level stuff so that we can go, okay, you can actually do research level physics in Lean. But then the other side is we try to formalize things which are related, which are taught in undergraduate physics, and try and do it in a way where you kind of hide all the complexity. This is quite difficult because there's a lot of things in physics where you get taught it at undergrad, and actually, if you go deeper into the underlying mathematics, it becomes quite complicated. So coming up with a good API and to make it as easy as possible for physicists. And I'm gonna speak about this right at the end. But AskMathLib is really great for undergraduate and student projects and master's projects. The aim is to try and make PhysLean also good for these sorts of projects. Good. Okay, so yeah, what has already been done? So let me give you the stats, and I've been lazy here, and I just put the website within the slides. So this is not as big as some of the projects or some of the libraries we saw yesterday, but it's also not a small project. It has 364 folders, about 91,000 lines, 2,111 definitions, and about 5,000 theorems. So obviously some of these theorems are small lemmas related to, to try and prove something within the physics, but most of the definitions and most of the lemmas are actually physics related. Yeah.
What are informal definitions?
Yeah, good. So informal so within PhysLean, I didn't write this in my talk, but this is good. So most physicists are never going to learn Lean, basically. And so the question is, how do you reap the knowledge of those physicists without allowing them to contribute to the project, without necessarily allowing them or without making them learn Lean? And we have done this using these informal definitions and informal lemmas. If you're familiar with Lean, you'll know these things called Lean blueprints. for like the Fermat/Theorem project, these are a very similar sort of thing, but they are written directly within the Lean code itself. But they're basically just English statements of definitions and theorems. The idea that the physicist could write them, not knowing any Lean, not even download in Lean, they could add those to the project, and then somebody later could come and formalize it. So it's kind of allowing the physicist to contribute to the project without learning Lean, and then perhaps somebody that knows Lean but knows less about the underlying physics and what to formalize specifically can come along and formalize them. So that's the idea about these. Yeah, these statistics are a bit backwards. So you really care about the number of informal definitions and the number of informal lemmas, not the ones that which aren't informal lemmas and definitions. But yes, okay. And yeah, and in a similar vein, we have a bunch of to-do items. I will explain, I will show you these later on. Good. Okay. So what's currently in PhysLean? This is a diagram. It's kind of blurry, so I apologize for that. But this is a diagram that shows you what is currently within PhysLean. I'll go through the main things. And I believe I didn't actually make this diagram. Flock made this, but I believe these are proportional to the size of the corresponding bars. So the biggest thing here on the left-hand side is quantum field theory. I am the main contributor to PhysLean, and my background happens to be in quantum field theory, so it's perhaps unsurprising that quantum field theory is the biggest block here. We have relativity here, and this is mainly special relativity, not general relativity. General relativity requires differential geometry, which progress has been made on in Lean, but we're not quite at the point where we can do general relativity properly. This block here is particle physics. I realize that people watching on Zoom will not be able to see me point, but hopefully they'll be able to see the slides better. So this block here is particle physics. This includes things like the Higgs boson potential, some of the stuff that we saw earlier. We've got string theory up here, perhaps the area of physics which is closest to mathematics if you ignore topological field theory, for example. And then we've got quantum mechanics, electromagnetism, space and time, which is basically like, you know, basic definitions and basic API around space and time. Units, there's long discussions on the Lean Tulip about units and the best way to do this. Physical mechanics, classical mechanics, condensed matter theory, some stuff on optics, and down here we've probably got some little stuff on thermodynamics and cosmology. So yeah, we kind of got some coverage in a lot of areas, a lot more coverage in some areas than others, basically down to a personnel issue. Yeah.
Is there any link between those parts?
Yeah, so everything is linked together. So for example, everything here depends on the stuff in space and time, because, you know, everything depends on that. Stuff in particle physics obviously depends on stuff, well, obviously it depends on stuff in quantum field theory. Relativity is used whenever you're dealing with things above close to the speed of light. So yeah, the aim is that you have everything connected. Everything should only be defined once. We don't make multiple definitions of things. In the same way that MathLib doesn't have multiple definitions of things like the reals.
How do you handle units? Do you use the typing system of Lean for the units?
Yeah, so there's multiple ways of doing this, and there's different ways currently. This is kind of a new addition to PhysLean, and there's big discussions on the Tulip about different ways to do this. Currently, the way that it's done in PhysLean is that you define a unit by how the quantity scales under a change in a choice. So for example, the unit of length within PhysLean corresponds to a choice of metric, translationally invariant, rotationally invariant metric on spacetime. And that gives you this distance, which then you say a quantity has this dimension under this unit if when you choose that metric and you choose another metric and you go between them, it scales in a particular way. And that gives you a definition of units that is independent of the type system. But then you can implement on top of this units where you're correct by the type system. So you have both sides, which you have like the underlying core definition of a dimension from physics. Then you have the type theoretic ability to stop you writing dimensionally incorrect statements. So that's the idea. Okay, I am going to quickly go through some specific examples of things that we have formalized. Perhaps the most simple example of a physics thing is the classical harmonic oscillator. So the classical harmonic oscillator corresponds to a point mass on a spring connected to the origin, and what happens is if you let the point mass go, it oscillates. And if you assume no damping, it basically oscillates in a sine curve or a cosine curve. So we formalize that. We have formalized the case where you replace classical with quantum. So that's the quantum harmonic oscillator, again, a point mass on a spring, but now you consider things to be quantum. And that means the energy of this point mass can't be anything, it has to be quantized. This is actually quite difficult because the quantum mechanics of a harmonic oscillator requires infinite dimensional Hilbert spaces. It requires these things called Schwartz maps and unbounded operators. And most physics textbooks skip over this stuff. And so if you want to do this properly, you really have to be real careful to do it in a way that, you know, still looks like physics, still has a physics intuition, but you're dealing with lots of things that the physicists may not be so familiar with. We've got Maxwell's equations. Maxwell's equations obviously predicts that if I turn this torch on, why you can see it and how waves propagate through free space and how basically all electricity is generated. We have Maxwell's equations both for functions and for distributions. So, you know, physicists like these things called Dirac delta functions. They like assuming things are point particles. If you want to do that properly, you have to use distributions. And again, a lot of what we're trying to do is making sufficient API around things like distributions such that physicists can use them while still believing that they are functions. And we're quite a long way from that point, but that is the overall aim. We've got the Lorentz group. The Lorentz group is the most important group in relativity. It is the group that describes symmetries of the world. So this is basically what most of this file is. We've also got index notation. So Einstein's summation convention, where you have two indices and physicists assume that you're summing over them. We've got that for both what are called bosons and fermions. We have the twin paradox in relativity. This says that if I start here and I walk in a straight line to here, compared to if I start here and I walk in a not straight line, then I will, even though I've taken the same amount of time to get from point A to point B, if I walk in a straight line, I will have aged less than, no, I would have aged more than if I walked in a curve. This is a consequence of relativity, and we have a formalization of that. This is more of akin to trying to get students involved, because twin paradox is something that students learn quite early on. It's not a paradox in any sense of the word. The tight binding chain is something in condensed matter physics. It's basically a finite dimensional quantum mechanical system. So unlike the quantum harmonic oscillator, which is an infinite dimensional quantum mechanical system, the tight binding chain is a simple, finite dimensional quantum mechanical system where you can prove things, and it's used in condensed matter physics. Anomaly cancellation. This is what quite a big chunk of actually this particle thing here is. What is anomaly cancellation? Every particle in the universe carries an electric charge. I'm simplifying a bit here, but yeah, so every particle in the universe carries an electric charge. For example, the electron carries a charge of 6. Those numbers, those electric charges that particles have, cannot be assigned arbitrarily. They have to satisfy a set of Diophantine equations, polynomial equations in the integers. And these Diophantine equations are called the anomaly cancellation conditions. And when my PhD was basically solving these Diophantine equations. So this happens to be why there's stuff about anomaly cancellation in PhysLean. And this is research level things. We've got Wick's theorem, which is what I mentioned earlier. Wick's theorem is the precursor to Feynman diagrams. So you may have seen these Feynman diagrams. They're like diagrams where you have maybe two particles go in and a squiggly line between them. They are what govern particle physics. They are what control the collisions that happen at CERN. So Wick's theorem, which is the underlying theorem behind why we have Feynman diagrams, is kind of the precursor to be able to make an API around Feynman diagrams and allow people to do, draw pretty pictures and write formal stuff about Feynman diagrams. We've got some stuff on string theory, which is up here. I'm not going to go into too much detail about that, but to say that, yeah, we're formalizing research level results in string theory, basically related to, types of F theory, if you know what string theory is, which I assume most people don't. So I'm going to skip over that. Good. We also have infrastructure, and we're gonna have a talk about Lean Explorer later. This is not my project, but we have this infrastructure that allow people to search. And Justin, who made Lean Explorer, luckily put PhysLean into it. So you can search for things like the Higgs boson, and you can get results about the Higgs boson. And this doesn't require any Lean to search. I'm not going to go into too much detail about this because we'll hear more about it later. We've got notes. This is kind of was a thing, and then it became difficult to maintain. But the idea is to write notes using Lean's Verso project that the physicists can look at, for example, for the quantum harmonic oscillator, and interact with because it's all connected to the underlying Lean code. And something like this is obviously a lot more friendly to a physicist than it is than some Lean code. We've got this to-do list, and this is what I mentioned earlier about these informal lemmas and informal definitions. We've also got these sorry for results, which are basically results of Sorian, and this is automatically generated from the Lean code itself. And the idea is that people that don't have a Lean background can come along and write these informal results, and then people can come and formalize them later. This is quite difficult because you kind of need to train the physicist, and including I need to train myself, so that when they're writing these sorts of results, they need to bear in mind what is the sort of knowledge base of somebody that can come and formalize it, write the things in a way that is more mathematical than they perhaps would if they were writing to a group of physicists. Good. So let me talk about the challenges. What are the challenges in formalizing physics? Obviously, there are challenges in formalizing mathematics. So I'm really going to focus on what are the challenges in addition to formalizing mathematics that you get because you're now formalizing physics. So the first one is something I like to call definition distance, and I'm by no means the first person to mention any of this. So imagine we have a quantity x, and we've got a space of acceptable definitions for this quantity x. And within this big space, which is this rectangle, we've got a space of acceptable Lean definitions. This quantity x might have an acceptable mathematics definition, and it may sit outside of the region of acceptable Lean definitions. And when you're trying to formalize a maths definition, what you have to do is you have to take that math definition and move it to the region of acceptable Lean definitions. Obviously, this is very heuristic. There is no such thing as a definition space of quantity. But when you're trying to formalize a definition from physics, it is more often than not the case that the physics definition is way out over there somewhere, nowhere near a Lean definition, and sometimes nowhere near a definition that would be acceptable even in a maths paper. there are whole areas of research that try and take physics definitions and try and formalize them and try and write them as mathematicians. Yeah.
Could you give an example of some definitions from physics and that is very difficult to formalize?
Units being one of them.
Sorry?
Units. Like, yeah, so dimensions of units.
Okay.
Other examples include, I mean, okay, there are lots of examples from like quantum field theory where, you know, people kind of have a way of doing things which isn't mathematically, like no one's thought of the underlying mathematical, the rigorous mathematical formulation. Even on a simpler case, like let's take quantum mechanics, the definition of a quantum harmonic oscillator. If you look at a physics textbook, it will define the Hilbert space of quantum harmonic oscillator as square integrable functions. That's not the right Hilbert space of quantum harmonic oscillator. It's something like everywhere equivalent classes of almost everywhere equal equivalence classes of square integral functions, dot, dot, dot. So the sorts of definitions that you see in the physics literature are often even missing details because they're just not that important to the underlying physics. Yeah, or so in some cases, no one's ever thought of the underlying mass definition. And there are examples of this. So yeah, so often the case. So there are whole areas of physics. People make their livelihoods out of taking these physics definitions and turning them into suitable mass definitions. So part of my old research was taking stuff related to things called generalized symmetries and using higher category theory to write that in terms of fancy mathematics. So when you're trying to formalize stuff from physics, you either have to bridge this gap from physics to mathematics, and then from mathematics you go further to lean, or you have to do it directly to lean. But in either case, the physics definition tends to be a lot further away from acceptable lean definition. So that's reason number one, and I realize I'm running out of time here, so I'm going to speed through this. Reason number two is that, let me zoom in, is that physics papers are often, oh, I can't zoom in. Okay, this is a maths paper. This is written in terms of definitions and theorems on the right. This is a physics paper. It's one of my papers. It's written as akin to like Moby Dick. It's written in terms of words, in terms of prose. Trying to extract definitions of theorems from this and writing that into lean is much more difficult than trying to extract definitions of theorems from something that's already written in terms of definitions and theorems. So that's difficulty number two. Difficulty number three, physicists like imprecise results. They like hand waving, they like, you know, let's assume this is zero, let's just assume these things are equal. Some of them can be formalized, you know, some of them actually have precise underlying physical meaning, but but in other cases, you know, you really do have to think about what is the physicist trying to do here? Is that allowed mathematically? Physicists like specifics, not generalities. They like specific 3x3 matrices with given entries. They don't like n×n matrices with given properties. Something like lean tends to be better at the generalities and worse at the specifics. In particular, it's not really a computer algebra system yet. So that is another challenge. Physicists like long computational and, I put in quotes, experimental proofs. They like writing computer programs that prove things. They like proving things based on the fact that things are small because of experiments tell us that is true, and things like that. And obviously these sorts of things are difficult to formalize. Good, okay, let me go on to what does the road ahead look like? And I'll quickly state these. We want to make a PhysLean game that will help people get involved in the project, that will help, you know, be that bridge for physicists, something like the natural numbers game, but that will help people get into the project. Improving documentation, you know, documentation is really key, and especially for this sort of project where you need to include that physics context within the project. Making better API around key areas, for example, you know, spherical coordinates, distributions, the sorts of things that the physicists kind of work with on a day-to-day basis, but kind of know how it works, but don't necessarily know the underlying details. And making sure the projects, I'm big for, as I kind of mentioned earlier, for making this successful, making this easy for students to contribute to. Like with MathLib, there is lots of scope here for students to engage with the projects and get involved, whether they're from a physics background, a maths background, or a computer science background. Okay, so yeah, thank you.
What about axiom system? Do you need some axiom somewhere?
No. So yeah, this goes back to what I was saying earlier. We're trying to formalize what the physicists do, not trying to axiomize it in some given axiom system. So we cut for a lot of formalizations, basically just to do something, you kind of have to pick a starting point. And usually that starting point can just be phrased in the sorts of stuff that is in MathLib. So it doesn't require any, for maybe like a given theorem within physics, you can write down, what are your assumptions, what are your axioms for that theory. But the project isn't governed by a set of rules, basically because, you could do like axiomatic quantum field theory, but then you're restricted to a very small subset of physics.
Did you manage to get any physicists interested in this?
Yeah, so there are a few physicists. So I've spoken to physicists in the past, and they're keen. The way to sell this to physicists is very much from the AI point of view, because there's a lot of work on, how do you do theoretical physics with AI, so that they get excited from that point of view. But yeah, we have a couple of physicists that contribute to the project. We have a lot of people that have come to the but yeah, I was saying to people earlier, we have a lot of people that have come to Lean to do PhysLean, and that have come from a physics background to do PhysLean. And this is kind of, this is good in the sense that they're there to do work on physics. That. Do you use PhysLean? So we want to use PhysLean. We have this thing I was saying to people earlier as well. It's really hard. If we use PhysLean, we'd have to import PhysLean, and then we would have to coordinate upgrade and then bump in Lean together. So PhysLean bumps with every month with Lean, and we would have to coordinate and bump PhysLean at the same time, and it gets tricky. PhysLean, I believe, I could be wrong, also has sorry results, has sorry in it, whereas PhysLean doesn't have sorry. So everything in PhysLean is proved, except if you attribute it with sorry form, and then it depends on the sorry action.
Physicists have a very particular way of doing computations. You have like infinitesimal all over the place. You reason a lot about what's negligible, all sorts of things like this. And there's a lot of kind of physical insight as to how to handle equational reasoning.
Yeah.
Are you able to reproduce at least some of that in PhysLean, or do you have to kind of turn everything into questions about distributions and then do the usual math way of handling it?
Yeah, I don't have an example of where we have done that. So yeah, I can't answer to how easy that would be, basically. But I think like there will be like if it has a nice rigorous mathematical formalization, then it should be possible to obviously do it in Lean, and then it's just a case of building the API to make it as easy as possible, so that the physicists don't have to worry about the details. But yeah, this is something that is still open, and how to best do that.
You mentioned the link to experiments.
Yeah.
It could be also unit test for your if you have computation.
Yeah.
You could try that.
No, so Yeah, this link to experiments I haven't particularly looked into that much yet. I mean, the most ideal case will be, you know, what physicists do in like particle physics, they write down a model and then they do some calculations and then they go, is this model excluded by experimental data? Yes or no. So stuff like that, where you can somehow feed the experimental data within the into the theorem to have something like, is this theorem good based on experimental data or not? If that's the sort of thing you mean.
Thanks. We need to move to the next talk.